Hey guys, this week we're going to be talking about solids and liquids. As you recall, the last couple of weeks we've been talking about gases and how they expand and their volume and how they relate to each other. And now we're going to move to solids and liquids, where we're going to see how they are described through this kinetic molecular theory. In front of you should have a packet of notes, and they'll be similar to the ones that I will be going over. I'll be talking through them, and you can just make some notes on the side as we're going through it. The first thing we're going to start talking about is liquids. You should know that liquids obviously have a definite volume. They take the shape of the container they're in. So it doesn't matter if you have a beaker of water, 1 milliliter of water in a beaker, or 1 milliliter of water in a test tube. They still have the same volume, 1 milliliter, but they take a different shape, one in a test tube and one that's more circular like the beaker. The properties now of this are described in this kinetic molecular theory. And you look at that on the middle part of your page there and see that particles are always in constant motion with liquids. They're interfering a little more often because there's more of them involved than it is in a gas. Gases are more spread out, and when they're more spread out, they don't hit each other as often. Okay, so the particles then are packed closer together, and then when they are, this decreases the amount of kinetic energy they have, and then this decreasing then increases the attractive force because they are more attracted to each other. If you think about a water molecules attract each other compared to gases that kind of just pass by. So this is how the kinetic molecular theory is involved in liquids compared to that of the gases that we've already discussed. Now, this allows for these intermolecular forces of this liquid to remain in order. Okay, and so as these gases these liquids stay in order, it stays in this liquid form. If you think about when you're trying to pour something, water kind of flows. You can see behind me this flowing water here. Water is in constant flowing motion, okay, because these particles are stuck together. Compared to like air, where you really can't see a lot of the gases, but you can tell that it doesn't flow as much as what a liquid would. And this is why we call liquids a fluid, because their ability to be able to flow and their attraction to each other. Now this takes place, another thing, of their density. Now when particles, the closer packed they are together, their density is going to increase. If you think of a solid rock, okay, something that is very solid, the particles are very, very close together. It's a lot denser, and therefore, if you ever put a rock inside of water, what's it going to do? It's going to fall to the bottom. Okay, because that water is less dense, it's not going to allow that rock to float. Liquids usually are less dense. They're less dense than a solid, but they are more dense than a gas. Because if you think about the way that the particles are shaped and how they are arranged, the closer packed they are together, the more density you are going to have. So it's like more particles per square inch within that substance that you're talking about. Now, if you turn the page, you go to your second page, okay, the ability to diffuse. Now, if you remember in chapter 10, we talked about diffusion rate and the rate at which gases diffuse with one another. And when they diffuse, that means they're going to mix, okay, and they can mix with one another in diffusion, or they effuse when they leave a certain container. Now, liquids are in constant motion. Okay, and the reason why they're in constant motion, their rate of diffusion is actually going to be slower. Okay, liquids have more particles, therefore the more particles they are going to have more movement. And when you increase temperature, okay, you're increasing that particle movement, and in an increased particle movement, you can increase your diffusion. Okay, so diffusion rate is going to be related based on the size of those particles. So you have some liquids that have larger particle sizes that are going to require higher temperatures, therefore faster movement to increase that, compared to those that are smaller in particle size. Now there's also a thing that we call surface tension. Now if you think about surface tension, I want you to think about a penny. And if any of you have ever tried to take a penny and you take water and you try to fill the penny up with water, you're going to create a dome shape over that. Okay, and that is because of all those hydrogen bonds. If you remember talking about chapter 2, 3, the hydrogen bonds allow them to bond together. And when they bond together, they create this tension with each other, and they attract. Okay, and it creates a dome shape and you can get like 30 drops of water onto one head of a penny, okay? And that allows us to have what we call a very high surface tension because of those hydrogen bonds, and it increases that force of attraction on there. We have a capillary action. So if you think about capillary action, it goes back to what we kind of learned in biology about water and how water is able to go from the roots, okay, under here and go up, which means it defies gravity. And how does it do that? Well, it's from the capillary action that it has. It is able to go up the stems, okay, of plants, and with that tension, it's able to defy that gravity of always wanting to try to pull it down. All right. On the next page of a liquid, okay, evaporation and boiling point. Now, we're going to go through different phase changes towards the end of the week, and maybe once I even get back to see you guys, we'll be going through the different phases of phase changes. And liquids can go through two types of phase changes. They can go from a liquid to a solid, okay, so you think about water, freezing it, okay, going down, and it's going to go to a solid. Or you can go from a liquid to a gas, which we call vaporization. Now, vaporization is the process that particles can escape from the surface of a liquid that's not even boiling, okay? So if things that vaporize, if I were to put a drop of water on a surface and come back the next day and it's dry, it vaporized. It didn't evaporate. No heat was ever placed upon that liquid in order for it to evaporate. It vaporized just through the process of it being there and entering itself into the gaseous state. Now, why is that? Well, particles of liquid have different kinetic energies, okay? Now remember, if we increase in the kinetic energy, that's like increasing your activity, okay? The faster that you go, the faster the particles move. And the faster that particles move, they can overcome these forces that allow them to stay in a liquid. Have you ever seen a boiling pot of water, okay? A pot of water that boils, that water is moving. And as that water is moving, it's increasing the amount at which those particles are moving inside. And if the particles are moving faster, the energy is moving faster. And as the energy is going faster and faster, okay, it's increasing its rate at which it can change state. So that would end up making it overcome its molecular force of wanting to stay as a liquid and transfer into a gaseous state where the particles are more spread out. Now we have boiling, okay, and that's when we're coming to that boiling liquid vapor that I was telling you about. Now if we go opposite of that would be cooling of the liquid. So you can condense actual gaseous vapors. And I don't know if any of you have ever been in a place where it is condensed on a window. And as you have that condensation on a window, you have a change in temperatures from the outside to the inside of that window. And as condensation occurs, you're coming from the gaseous state and forming liquid. And then it can keep going down as you drop and you increase those attractive forces. So as you decrease the temperature, your attractive forces are going to increase. So that should also lead you into what we're going to talk about when we start talking about solids, is that as we go down and decreasing that temperature, your attractive forces become more and more and more, and then therefore you're going to increase your density and increase the amount of the way the particles attract to each other and go then from another phase change from a liquid then to a solid, okay? So what I'd like y'all to work on after this presentation is finished is you have a worksheet from section 1 from chapter 12 that I'd like you to work on, and when we return to school on Thursday, we will go over that and check your answers. So y'all have a great day and think about liquids.